Okay, so anytime we form a bond, one of the things that we're going to need to think about is the electronegativity difference. Now, we discussed electronegativity briefly before. Again, that's the strength of attraction for a given atom for an electron in a bond. And we showed that fluorine was the most electronegative atom, and the electronegativity increases from left to right and bottom to top, mainly due to effective nuclear charge and, of course, size. The only one that's sort of out of place is hydrogen, and that sort of sits right next to boron, 2.1 value for electronegativity. Okay, so it turns out that this will also be a tool to using it to determining if a bond is going to be an ionic bond or a covalent bond, and more importantly, this is going to lead to some ramifications for molecule polarity, and set up a lot of information we're going to need for intermolecular forces. But right now, what we're going to see is that differences in electronegativity cause an unequal sharing of electrons within a covalent bond, and of course, if that difference is too large, it actually turns into an ionic bond. Okay, so let's take an example of that HF molecule. Okay, we know that hydrogen and fluorine, HF, going to share 2 electrons. Hydrogen's okay with the duet. Fluorine's has its octet rule. Okay, but we can see that hydrogen has an electronegativity value around 2.1. Fluorine, the most electronegative atom, 4.0, there is a very large difference in electronegativity. And so what this does is it sets up a scenario where within a molecule the electrons have a stronger attraction towards the higher electronegative atom, fluorine. Okay? And a less strong attraction to hydrogen, the least electronegative atom. So most of the time electrons are going to be crowded around the fluorine atom. Okay, which causes a higher electron density around the fluorine atom and an absence of electron around the hydrogen atom. Okay, what this does is it sets up a dipole moment or a polar bond where, just like sort of you can think of the poles of the Earth, there's 2 poles. We can 2 distinguishable ends of this molecule. We have one end that has an experimentally observable partial negative charge because of the higher electron density associated around the higher electronegative atom. And because of the absence of electrons near the hydrogen, the less electronegative atom, there is a partial positive charge. And we denote these partial charges with the small lowercase Greek letter delta. Delta negative for partial negative, delta positive for partial positive. Okay? And at various times we're also going to want to indicate the dipole moment, and what we do is we draw an arrow towards the most electronegative atom, and I usually remember that by we keep the positive end or a little hash mark next to the less electronegative atom or the most electropositive atom. Okay, so this difference in electronegativity sets up a dipole moment, which in a sense is called a polar bond, as we will see. Again, this phenomenon is experimentally observable if you have an HF solution in a beaker and you put in 2 electrodes. If there's no charge in those electrodes, no potential field, these HF molecules are going to be randomly oriented. If you apply a potential to those electrodes and create an electric field between them, the HF molecules, all of the HF molecules will line up so that the partial negative charge is associated or attracted to the partial or to the positive electrode, and the partial positive charge will line up so that it is attracted to the negative electrode. Okay, they'll line an electric field. Okay, so just how big of a difference in electronegativity do you need to set up a polar bond or partial negative and partial positive charge? And it turns out that there is some degree of certainly you have to take it by case basis sometimes, but nominal values for setting up a polar bond or other bonds are listed here. Usually if you are between 0 and 0.4, the electrons are shared equally, the difference, delta En. So the subtraction, you subtract the lower electronegativity value from the higher value to get a difference. And if that value is between 0 and 0.4, generally we associate those with a molecule that you cannot tell where those electrons are at any given time. They are shared equally among the atoms. Okay? And we would call this a non-polar bond. Okay? If you have electronegativity values greater than 0.4, but less than 2.0, you set up a dipole moment. Again, we would show that with an arrow pointing towards the electronegative atom, where we have a partial negative charge and a partial positive charge, and you can tell there are two distinguishable ends of this atom, or two poles, and this would be a polar covalent bond. And again, anything greater than 0.4 up to 2.0. If you have a difference in electronegativity so great that you are in the range of 2.0 to 3.3, the more electronegative atom has such a strong attraction for that electron, it not only unequally shares it, it actually will just take it, and it will create an anion and a corresponding cation. Okay, so how do you do these? Going to look at those values on the previous table, the first table of this video lecture, and you're going to calculate the change in electronegativity. So let's do it for a carbon-oxygen bond. Okay, we look up the electronegativity value for oxygen. That's 3.5. The electronegativity value for carbon, that's 2.5, always subtracting the lower from the larger value to get a positive value. And we get a difference electronegativity of 1.0. And so any carbon-oxygen bonds are always going to be polar bonds. There will be a partial negative charge associated with that oxygen, a partial positive charge associated near the carbon atom. Okay, let's look at the value for a carbon-nitrogen bond. Okay, nitrogen has a electronegativity value of 3.0. Carbon is still 2.5. That will give us a value of 0.5, and again, that's greater than our 0.4 cutoff. And so this value will be polar. Okay, one more example with carbon. Let's do a carbon-hydrogen bond. Okay, carbon now will be the most electronegative atom, 2.5. Hydrogen is 2.1, and so that gives us a value of 0.4. And this will be our cutoff for the nonpolar polar bonds, and a carbon-hydrogen bond is always, always, always nonpolar. Okay, one last example. Let's look at a lithium chloride bond. Chlorine has electronegativity of 3.0. Lithium has an electronegativity value of 1.0. And so that gives us a value of 2.0. And so this turns out to be an ionic compound. The strength of the electronegativity of that chlorine atom is so great that it actually just removes the electron from lithium and sets up a ionic bond. Okay, so again, we'd always look back at this sort of continuum of bond types to give us an idea. Some of those values around the borders are sometimes a little bit trickier. If we're looking at 0.4 for carbon-hydrogen, that's always going to be the cutoff. That's always going to be a nonpolar bond. Around 2.0, it can sort of go either way. It usually tends to go to the ionic side of things. And one other trick that we can use to sort of break any tiebreakers is that, in general, if we have two nonmetals bonded together, such as hydrogen and fluorine, they tend to be covalent bonds. Okay, if we have a metal and a nonmetal, such as lithium and chloride or sodium and chloride, they tend to be ionic. Because you can see that as we go across the period, our electronegativity different increases. So when we have nonmetals bonded with metals, usually those values are quite high. So this is a good characterization of covalent and ionic bonds.